This week, you'll learn how to create your very first computer program. But first, some questions. Have you ever given someone directions to go from one location to another? Or have you ever taught a friend how to carry out a task? For instance, how to tie their shoelaces? Or have you ever followed a recipe, for example, to bake a cake? If your answer to any of these questions or to similar questions is yes, then you're already familiar with programming. You just haven't realized. Let's start by exploring different examples from everyday life. These examples will show you the fundamental concepts of programming. Let's say we want to teach someone how to make a sandwich. We can describe the steps as: take 2 slices of bread, place a slice of ham over one slice of bread, place a slice of cheese over the ham, place a second slice of bread on top of the cheese, and that's it. So if we were to write down the different steps in English, that's what it would look like. You can see that we describe this process as a sequence of steps, which are followed in order, one after the other. Let's look at another example. We want to describe how to change a light bulb. We could do the following. If you don't have a new light bulb, buy a new one. Turn off the power. Repeat twisting the light bulb counterclockwise until you remove it. Throw out the burnt light bulb. Place the new light bulb into the socket. Repeat turning the light bulb clockwise until it is tight. Turn the power on. And this is what this process would look like when writing it down. Here we have a sequence of ordered steps which also include a decision and a repetition. Sequence, decisions and repetitions are basic constructs with which we build our programs. We describe the process for making a sandwich and changing a light bulb as a step-by-step procedure. This ordered sequence of steps is called an algorithm. Algorithms describe the procedure for carrying out a task or solving a problem in a step-by-step fashion. They may include sequences, decisions and iterations, just like we saw in the 2 previous examples. Very often, there is more than one algorithm that effectively solves a problem. Let's have a look at the following map and try to give directions to a person who is currently at the hotel and wants to get to the train station. Can you come up with 2 algorithms for this problem? One option would be face north, walk 2 blocks, turn to the west, walk 1 block. Another option could be face west, walk 1 block, face north, walk 2 blocks. There are even more options, perhaps not as quick, but they can effectively solve our problem. As you might have noticed, the above algorithms have nothing to do with computers, and they can take lots of different forms. For example, the first algorithm that we came up with for going from the hotel to the train station can be represented on the map, in text, as a flowchart, or as computer code. Let's have a closer look at these. Here is the visual, map-based form of the algorithm. It clearly shows that we walk 2 blocks facing north and then 1 block facing west. The algorithm in English, the way we speak it, could look like this. Head north for 2 blocks, then turn to the west and walk for 1 block. Algorithms can be graphically represented with the use of diagrams called flowcharts. The flowchart that visually illustrates our algorithm is this one. We first face north, then walk 2 blocks, then turn to the west, and finally walk 1 block. This flowchart demonstrates the sequential character of this algorithm, with one step following the other. Would you like to find out more about algorithms? In the next video, we will analyze more interesting examples. Let's look at more examples of algorithms we use every day. How would you do the following? Cross a street, bake a cake, put a shirt on, pour a glass of juice, sum 2 numbers of 3 digits each, or even explain to an alien how to brush his teeth. In each case, it is important to think about the assumptions that we make. For example, What assumption are we going to make for the traffic when designing an algorithm for crossing the street? Is it left hand, like in Scotland, or right hand, like in Uruguay or Spain? We need to take into account the direction of the vehicles in order to check the corresponding side. Or, let's look at a more extreme example. What assumptions can we make when teaching an alien how to brush his teeth? Does he know what a toothbrush is? And does it matter how many teeth he might have? Oh, hi there! We would like to introduce you to Cody, who's going to be participating in this course too. Cody is from a different planet. So our first challenge is to teach him how to brush his teeth. We invite you to write down your instructions, like we did in the previous examples, and upload them in the discussion forum. See you later, Cody! After analyzing a problem and making any assumptions needed, we can go ahead and describe how to do a task. We should emphasize, however, that it is crucial to clearly detail our instructions. There might be steps which mean something different for different people. For instance, if when telling someone how to bake a cake, we instruct them to put it in the oven for a short time, they wouldn't really know at what temperature the oven should be, or how long a short time really is. Now let's do an experiment that highlights the importance of precise instructions. Find a pen and a piece of paper and follow the algorithm in the following slide to draw an object. Draw a diagonal line, draw another diagonal line connected to the top of the first one, draw a vertical line over the point where the diagonal lines meet, draw a horizontal line over the straight line, draw a diagonal line from the bottom of the first diagonal to the straight line, draw a diagonal line from the bottom of the second diagonal to the straight line, draw a curvy line starting at the bottom of the straight line. What did you come up with? The original object that we were attempting to describe was a kite. Did you draw something similar? The algorithm provided was quite ambiguous, so there were many ways to interpret it. And in fact, I would expect to see a wide range of drawings, the majority of which do not resemble a kite at all. Can you write a better algorithm for drawing a kite? Have a go and test it with your friends to see if it works. Or how about developing an algorithm for drawing some other object? You can upload your algorithm in the forum and your classmates can guess what it is. As this experiment showed us, being precise is very important when giving instructions to humans. And actually, it is even more important when programming computers. All the computers do is follow instructions. So if these are not clear, computers will probably not do what we want them to. If you think about it, computers aren't really that smart. Even though they're very good at some tasks, like doing big calculations and playing chess, humans are much better in others. For example, looking after a child, recognizing objects and images, and having a meaningful conversation are not that easy for a computer. Okay, so you've learned what an algorithm is and what it looks like, and you've seen a few examples from everyday life. It's now time to start implementing algorithms in Scratch. This is exactly what we'll do in the next video.